Today we start Chapter 3, and this is Section 1 in Chapter 3. 3.1 is called Exponential Functions and Their Graphs. The first thing we're going to do is review some of the properties of exponents that you learned in Algebra 1 and Algebra 2. These are important to understand and have at your fingertips. The first rule we have is a product rule, which is a to the n times a to the m. What you do if you have the same base, different exponents, you can add the exponents. So this is a to the n plus m. The second property of exponents is the quotient rule. If you have a to the n divided by a to the m, that is a to the n minus m. The third rule is the power rule. If you have a to the x taken to the y power, you multiply the exponents. So you have a to the x times y. And the fourth rule is a combination of a couple of rules. If you have multiple factors raised to a power, say you have a to the x times b to the y times c to the z power. So you have three factors inside parentheses and you want to take it to the m power. You're going to multiply each one of those exponents by m. So that results in a to the xm, b to the ym, c to the zm power. Another rule is if you have different bases, let's say you have a to the nth power times b, but you're bringing it up to the same exponent. This is kind of this rule in reverse. What you can do is you can multiply those two bases together, a times b, whatever they are, they can be numbers, and bring them all up to the nth power. The sixth rule is the negative exponent rule. A to the negative nth power is equal to 1 over a to the positive n power. The seventh rule is the fractional exponent rule. If you have a taken to the power of x over y, this becomes a radical, and the y is the index of the radical. The a is the radicand, and you can take a to the x power on the inside, or if you want to take the index is still y, so you can take the yth root of a and take it all up to the x power, either one. They're both the same. And so this is just a review of what you've learned in Algebra 1 and Algebra 2. And sometimes they get a little bit, sometimes you'll have to evaluate them in an unusual way. So let's say, for example, we have 3 to the x minus 2 power, and we're going to try to make that equivalent to another expression. What you can do is use that quotient rule. This is the same thing, or maybe you're asked to simplify this. So this is the same thing as 3 to the x divided by 3 to the second power with the quotient rule used backwards, which is the same thing as 3 to the x divided by 9. And you can rewrite that as 3 to the x all over 9, which is the same thing as 1/9 times 3 to the x. So if you look at this expression, 3 to the x minus 2, you should be able to come up with an equivalent expression of 1/9 times 3 to the x. Here's another example of using multiple rules. Let's say you have 10 to the x plus 4. Well, it's a similar example from the one above, but instead of the quotient rule, we're using the product rule. And so this says 10 to the x times 10 to the 4th, which is 10 to the x power times 10 to the fourth is a 1 with 4 zeros. 1, 2, 3, 4. So that's 10,000 if you don't have a calculator. And usually you'll put the coefficient in front of the exponential expression. So that's the same thing as 10,000 times 10 to the x power. So that's the same thing as 10 to the x plus 4. Another example, let's say we have 27 times 3 to the x power. And let's work backwards. Let's see if we can find an equivalent expression to that. Well, 27 is the same thing as, because I'm looking at this base of 3, well, I know 27 is 3 to the third power. 3 to the third times 3 to the x. And then using the product rule, you just add the exponents when you're multiplying two expressions with the same base. So this becomes 3 to the x plus 3. The next thing we're going to look at is the graphs of the parent function y equals a to the x. This is called an exponential function. And the requirement on the exponential function is that a must be greater than 0. A can't be negative, and a can't be equal to 0. You graph these parent functions in Algebra 2, and what we're going to do this year is we're going to graph them without a graphing calculator, and we're going to do all of the common transformations on it, shifting, reflecting, and stretching based on what we're given. The general format of a graph, or the general shape of an exponential function, y equals a to the x, is you'll have a y-intercept at 0, 1, because when x is equal to 0, anything to the 0 power is equal to 1. So it's going to come down like this, and then it's going to increase very rapidly. So that's the general shape of just y equals a to the x power, 0, 1. You have an asymptote on this parent function, and an unshifted, unreflected asymptote, or graph has an asymptote of the x-axis, which is y equals 0. And of course, what we're going to do with this is we're going to reflect it, shift it to the left, to the right, up, down, and so we'll get several different ones. Let's start out with specific function. I guess I'll turn over the page here. We'll do specifically y equals 3 to the x with no graphing calculator. If you wanted to set up a quick xy table of y equals 3 to the x, well, the domain is all real numbers, which means you can put in anything for x. Negative, positive, anything you want. But the range for y equals 3 to the x, if you remember, you had an asymptote of the x-axis, which makes the range of y is greater than 0. So everything is going to be above the y-axis, and we'll see that with our table of values. So for our table of values, we can just plug in x equals -2, -1, 0, 1, and 2. We'll get those 5 points. And 3 to the -2 power is 1 over 3 squared, which is 1/9. 3 to the -1 power is 1 over 3 to the first. Anything to the 0 equals 1. 3 to the first is 3, and 3 squared is 9. So those are our initial points that we're going to be working with. And I'll dot this x-axis, label it y equals 0. My y-intercept is 0, 1. So we have 1, 3, 2, 9, which is pretty much off the graph. Exponential functions increase very rapidly. And then -1, 1/3, and -2, 1/9 gets very, very close to the x-axis, but it's never going to touch it. So there's your just basic y = 3 to the x. And if we wanted to do any kind of transformation, let's say we want to graph y = -3 to the x power. Well, what does a negative outside the entire function mean? It means we're going to negate all of the y values, which means it's a reflection in the x-axis. So what we do is we take all those y values from our initial table, we make them all negative, and our new graph is a reflection through the line y = 0. And so we have -2, -1/9, -1, -1/3, 0, -1, 1, -3, and 2, -9. You might want to write down some of those notes that I'm saying. Reflect in the x-axis, which means negate the y values. That's not a very good graph, of course. All right, in this case up here, the range is y is greater than 0, but this case, the range is y is less than 0, but the domain is still the same. Let's say we want to graph y is equal to 3 to the -x power. Negative in front of the x means you're negating all of the x values, which means you're going to reflect in the y-axis. So if you take the table of values that we started with and create a negative, negate all of those x values, you get +2, 1/9, +1, 1/3, -1, 3, and -2, 9, which will just reflect our graph in the y-axis. We're still going to have the same asymptote of y = 0, but this time, instead of increasing, this graph is going to be a decreasing graph because it's coming down. Another name for y = 3 to the -x. This is also the same as y is equal to 1/3 to the x because of the negative exponent, which is the same thing as 1/3 in parentheses to the power of x. And we can shift things left, right, up and down also. And we can stretch and shrink just like we did all of the other functions the same way. But I want to talk about the difference between decreasing and increasing graphs. Decreasing graphs, as you're going from left to right, go down. So this is decreasing. The other example in this one, this graph was also a decreasing graph because it was going down as you're going from left to right. In this first example up here, this graph was increasing. We'll label this as decreasing. All right. Oh, and an important thing to note, I told you that the base had to be positive. I think I told you that. Yes, over in the beginning, a is greater than 0. This value of a is +3, but the negative is on the outside of the function, so you could almost put parentheses in there. You don't have to, but the base is still 3. You're just negating the whole function, so that still keeps that premise that a is always greater than 0. All right, if you have y = a to the x power, the difference between increasing and decreasing graphs is that if a is greater than 1, then the graph increases, or the function is an increasing function. which means the graph goes up. And on the other hand, if a is between 0 and 1, a's got to be greater than 0. But if it's in between 0 and 1, like in this example right here, a was 1/3 between 0 and 1, the function is decreasing. Let's just talk about the asymptote if you have a vertical shift. If you have a horizontal shift, if this whole thing is moving left or right, the asymptote still stays at y equals 0 because you really haven't lifted anything. But if you want to graph a vertical shift, like y equals 3 to the x minus 5, this shifts the graph down, which means everything is shifted, including the asymptote. So now the new asymptote is y equals -5. And other than that, everything, the domain is still all real numbers. The base being greater than 1 means this is an increasing graph. So this graph looks exactly like the original graph that we drew, but you're just moving everything down 5, which means you're subtracting 5 from all the y values. The next thing we're going to talk about very quickly is in Chapter 3.2. Chapter 3.2 talks about logarithms and their graphs. And an important thing to remember about logarithms, that a logarithmic function is the inverse of an exponential function. Oops. And remember, with an inverse, it just means you switch x and y. So for example, if you have y equals a to the x, this is your exponential function. And if you switch x and y, you get x equals a to the y. And then you had to solve it for y, if you remember from last year in Algebra 2. And in order to solve this equation for y, you get y is equal to the log, the base is a, and the argument is x. So this is the log function. A log function has the same types of rules that the exponential function has. It has a product rule, a quotient rule, and a power rule. There are 3 rules that you need to remember. You learned them last year. You're probably pretty good at them. The first rule is if you have a log function, the base can be anything. I'll just put a b for base. And if you have the log of a times b, this is called the product rule. You can split that log into 2 logs, which is the log of a plus the log of b. Oops, I shouldn't have used the same letter. You know what? Let's make this base a capital B so it's not the same exact letter. So this is the log base b of b. That's called the product rule, and it's similar to the rules of exponents because you add the exponents when you have the product rule for exponents. The second rule is that the log of a divided by b, or a over b, is the log of a minus the log of b. And then the third rule is the power rule for logs. If you have a log of a to the nth power, you take that exponent and you drop it down in front, and this becomes n times the log of a. And I'm going to stop right here because I think that's enough for today, and tomorrow in class we'll do some examples and get used to exponential and log functions.